In this section about multi-layer switching, I'm going to talk about inter-VLAN routing on the switch, I'm going to talk about the layer 3 ports, and I'm going to talk about the Cisco Express forwarding. Inter-VLAN routing is a solution to the problem of communicating between different VLANs. As we know, VLANs provide isolation between different hosts by putting them in different broadcast domains. So hosts in one VLAN can freely communicate to each other in layer 2 because they can see each other's broadcast, they can see each other's multicast and broadcast traffic, they can communicate directly without the help of any device between them. However, if we want to communicate between devices that are in different VLANs, we have to route that traffic. And this is really everything that inter-VLAN routing is all about. There are multiple approaches how to solve this particular problem. I divided them into two categories, the traditional approach and a more modern approach. The traditional approach is something that is called inter-VLAN router, where we have a router that has a port in each VLAN that we are using in our network. For example, let's say that we had multiple VLANs on our switch. So let's say that we had VLAN 10 with 3 ports here, and let's say that we had VLAN 20 here. If we wanted to communicate between host A here and the host B, we would somehow have to route the traffic between them because they cannot see each other. So using the inter-VLAN router, what we would do is we would put the router here that has 2 physical interfaces, and we would connect one interface in a port that is in VLAN 10, and we would connect another interface that is in VLAN 20. So if we wanted to communicate between host A and B, we would send the traffic out of this interface, this traffic would get routed on the router and would be sent towards the host B. And we would have similar traffic flow in the opposite direction for the traffic going from B to A. Now, this in itself is not necessarily a bad solution, but it's a solution that doesn't really scale that much. It doesn't scale because it may work if we have just a few VLANs, but if we have 10, 20, 200 or maybe even 2000 VLANs, how many interfaces would we need to have on this device? We would have to have unreasonably large number of interfaces. For that reason, there is a different solution that somewhat addresses this problem. This solution is called router on a stick. Router on a stick is pretty much similar solution to what we have seen now, except that the router that is connected to the switch does not connect using multiple physical interfaces, but connects using a single interface that has sub-interfaces, or it basically has a trunk connected to the switch and uses that one trunk to route the traffic between the VLANs. So, to take a look at that, let's see the same problem. So we have the switch, we have our VLAN 10, we have our VLAN 20, and here we have the router that has, this time, it has a trunk interface. So if we have host A here and host B here that we want to communicate, we are going to send the traffic out of this trunk. Now mind you, this is going to go out as VLAN 10. The router is then going to route this traffic and it's going to send it back as VLAN 20, sending it towards the host B. This solution does not require a large number of physical interfaces, but it also doesn't scale that much. It scales somewhat better than the previous solution when we have large number of VLANs, but if we have large volume of traffic, this solution is not necessarily good, because take a look. For the traffic going from A to B, we have consumed the bandwidth on this interface twice. Once we have consumed it in this direction, and the other time we consumed the bandwidth with the same exact traffic in the opposite direction. The only thing that changed were the VLAN tags that we used. So to address this scalability problem, there is that modern solution. A modern solution involves multi-layer switch. A multi-layer switch is really just a fancy name for a switch capable of routing, or if you want to be a little bit more cynical, is the fancy name for the router that has only Ethernet interfaces, fast Ethernet, gigabit Ethernet, 10 gig, 40 gig, whatever we might have, capable of switching as well. And this is going to be a really interesting solution to this problem, because right now what we can do with this particular approach, we don't need an external device. What we can have here are hosts that are, let's say, in VLAN 10 and in VLAN 20, and again we have our host A and host B, but this time it is the switch itself that has the routing capability. So if we have the traffic that goes between, let's say, hosts A and C that are both in VLAN 10, what's going to happen? This traffic is going to be switched at layer 2 here by our switch. But if we have traffic that needs to go from host A to host B, it is still going to go to our switch, but this time it's not going to be transmitted on layer 2 to our host B. It is going to be routed here in the routing engine on our switch, and it's going to be sent to host B. So technically speaking, hosts A and B can communicate directly to each other through the switch, but the process that made it happen is somewhat different internally on the switch. And this is where Cisco enlists the help of a process called CEF, or the Cisco Express Forwarding, which is an optimization of the routing that makes this equally quick, equally fast from the perspective of the overhead, the speed of switching, as if we were simply switching the traffic on layer 2. A much more interesting example to look at here is what happens when we have more than one switch involved. When we have more than one switch involved and we want to provide communication between hosts in different VLANs, there are again multiple approaches that we can use. A traditional approach would be something along the lines of, let's say, having switch 1 having ports in VLAN 10 and switch 2 here having ports in VLAN 20, and then interconnecting this with a trunk and creating and allowing VLANs 10 and 20 on this trunk, and creating virtual interfaces for routing the switch virtual interfaces, or SVIs, the VLAN interfaces on switch 1 that will be in VLAN 10 and VLAN 20, and doing the same thing here on switch 2. Now, the SVI interfaces are logical interfaces that exist on the switch only logically. They are not tied to any real physical interfaces. They are configured with the syntax of interface VLAN X, and then here we can specify the IP address just like we would on any other interface that we have. That way the traffic going, say, from host in VLAN 10 to host in VLAN 20 on switch 2 would go as VLAN 10 traffic all the way to switch 2, would arrive to this logical VLAN 10 interface. It would then be routed through VLAN 20 and sent out in VLAN 20 here. We would have a similar traffic flow in the opposite direction here, but this creates one tiny little problem. Why are we allowing VLAN 20 on this trunk when we have only hosts in VLAN 10 here? And similarly, why are we allowing VLAN 10 on the trunk when we have only hosts in VLAN 20 here? There is another approach that could be used in this case. This other approach is to use layer 3 ports. So we could have switch 1 that has all ports here in VLAN 10, and we could have switch 2 that has all ports in VLAN 20. And we could interconnect this with a simple layer 3 connection. Now, from the perspective of switch 1, the way switch 1 sees this is as if switch 2 was a router. From switch 2's perspective, this looks pretty much like this. So these hosts connected to layer 3 ports, they are not going to be switching the traffic. We are not going to be switching traffic to them. We are going to be routing the traffic to them. This, in turn, while it may solve this problem of unnecessary allowing ports on a trunk, it does create another problem. That problem is if we send traffic here towards switch 1, where is our default gateway? Well, the default gateway could be an SVI in VLAN 10, and here we could have an SVI in VLAN 20. So when we send the traffic towards our default gateway, which would be in this case switch 1, what does switch 1 do with this traffic? It needs to route it to switch 2. How does it know that? Well, it knows that because it may need to have some sort of routing information presence, just like any two routers would behave in this case. So we may need to run some routing protocol like EIGRP or OSPF or even BGP, or we might have just simply static routes in place. But we need some sort of routing information to be exchanged here. Exchanged or to be present on both switch 1 and switch 2 to send this traffic across. But layer 3 ports as a concept are also very interesting. Sometimes we just may want to communicate with a particular host, and we don't want to have multiple hosts on this VLAN. So why would we waste a VLAN? Why would we waste the configuration steps that are required to configure an access port, create an SVI, and do whatnot, and maybe filter the traffic on the trunks towards other switches? In order to avoid doing all that, we can just configure port as a layer 3 port and connect the host to it directly. It doesn't have to be the connection between the two switches. So how do we configure layer 3 ports? Well, it's very simple. All we have to do on the port is no switch port, and that port is suddenly a layer 3 port. Let's now see the configuration of layer 3 interfaces in action. What I'm going to do to show you that, I'm going to build a very, very simple network. It's going to consist of a single switch, which is going to be my Cat1, which is going to be connected to a host, which is my Linux host that usually runs Wireshark in these videos that I'm making, but it will work as just a regular PC in my case. So this is going to be Fastnet 03, and I'm going to have network 192.168.100.0/24 between them. On this side, I'm going to have an IP address that ends with 100, the last octet will be 100, and on this side, I'm going to have .1. Now, what I want to try here is to configure this interface, Fastnet 03, as a layer 3 interface and simply ping my host. And in the process, I'm going to show you a thing or two as well. The first thing that I'm going to do is, obviously, I'm going to go ahead and configure my Fastnet 03 as a layer 3 interface. The configuration to do that is very simple. It's no switch port. Now, let me show you how the output of show interface Fastnet 03 switch port is going to look now. You may recall that the command show interface and then interface identifier switch port is going to show me all the layer 2 parameters of the port. In the case of a layer 3 port, the only thing it shows is that switch port is actually disabled. And this indicates that this is a layer 3 port. This port is down at the moment, but I'm not done configuring it. What I want to do is I want to configure an IP address on this port as well. So I'm going to say IP address 192.168.101/24, and I'm going to say no shutdown. When the interface comes up, I should be able to ping my own interface. I should be able to communicate with the other side, but before I do that, I should check my routing table. So if I want to check the routing table, I'm going to say show IP route, but what I'm going to get may be a little bit unexpected result. It is going to show me no routes. It's not showing me any connected routes. Now, the reason for this is that at this moment, this switch, my Cat1, is configured to operate as a switch with an IP address. That IP address is working just like an IP address on a host would, just like it would be on a server or on a workstation running Linux or Mac OS or running Windows, and it's not operating as the router. Show IP route is going to show me the route information base, the routing table, which does not exist on this host. Now, I can make my switch work as a router if I enable IP routing process, which on traditional routers is turned on by default. On most Cisco switches, it is actually turned off by default. So I can go in here and I can say IP routing, which is going to enable me to actually see my routing table. So now I'm going to get the output that I was hoping to get, that 192.168.100/24 is a directly connected network on Fast Ethernet 03 interface. Let me turn off the IP routing process. I want to turn off the IP routing process because I want to show you how my IP communication with my Linux PC is going to work without IP routing process being enabled. So what I'm going to do now is I'm going to say ping 192.168.101. This is pinging my own interface, and I should be able to ping the other side. And I can see that I can successfully ping the other side. Let's go to Linux PC and try to ping the other side as well. So I can ping my switch, which is a good thing. So I have the communication between my Linux PC and my Cat1. Let's add one more thing to the mix. What I'm going to do now is I'm going to add Cat2 to the mix. So my Cat2 here is also going to be connected to Cat1 on, let's say, Fast Ethernet 24. And I'm going to have this configured also as layer 3 ports. And let's say that the network that I want to use between them is going to be 192.168. Let's say 0.0/24. I want to use .1 here and .2 here. So I'm going to have layer 3 ports all the way. So let's go and configure this on my Cat2. To do that, obviously, I'm going to need Cat2. So let's go ahead and configure Cat2 first. I'm going to go to interface fastnet 24, and I'm going to say no switch port. I'm going to say IP address 192.168.0.255.255.255.0, and I'm going to say no shutdown on that port. On Cat1, I'm going to say interface fastnet 24, no switch port, IP address 192.168.0.1.255.255.0, and I'm going to say no shutdown here. So let's see if I can ping between them. So if I do ping 192.168.0.1, I can ping my own interface, and I can ping .2. Now, this first ping that failed, this one here, don't be alarmed about it. This is just an ARP timeout. So let's see from Cat2 if I can ping 192.168.0.1, I can ping the other side, and I can ping myself. Now, let's add on Cat2 a default gateway pointing to the IP address of Cat1. So I can do that by saying IP default gateway 192.168.0.1. So now, if I do show IP route, what I'm going to see is that in this output here, it says that the default gateway is set and it's 192.168.0.1. So my Cat2 should be able at this point to send the traffic to Cat1 and to my Linux host, and Cat1 should know what to do with this traffic. Now, what I'm missing is perhaps a default route or a route back on a host towards Cat2. So what I'm going to do now is I'm going to go add that route, and I'm going to come back, and I'm going to show you something very, very interesting. I have now added the route that I was missing on a host, and let me go to the host and let me try to ping 192.168.101. This is the IP address of the Cat1 directly connected to the host. So from the host, I'm now trying to ping this IP address here. There is no reason for this not to work. And when I send the ping, I can see that I'm actually getting the responses. Let me try now to ping 192.168.0.1. Now, this address is this interface here. So from host, I'm now going to try to ping this IP address here. If I send this ping here, I'm still going to get the responses. The responses are sent by Cat1. Let me now try to ping this host address here. So I'm going to try to ping 192.168.0.2. If I do that, I'm going to see no results, which means that traffic is actually being dropped. I can see here that I transmitted 6 packets and that I have received 0 packets, which means that I had 100% packet loss. The reason for this unusual, seemingly unusual behavior is very simple one. What is happening here is, remember, cat1 is just a host. It's not acting as a router. When I send the ping to this IP address here, the switch knows how to respond. When I send ping to this address here, which is also one of the addresses of switch 1, the switch 1 knows how to respond. But when I try to send the traffic that's supposed to go through cat1 and out to cat2, this traffic is not going to be transmitted because IP routing is not enabled on the host. So let's enable it. Let's enable the IP routing functionality on our switch. So going back to my terminal, on cat1, the command to do that is very simple. Remember, IP routing. This is the only thing I have to do. So when I go back now and I start sending the ping, now I can see that ping actually works. Like I mentioned before, of course, using layer 3 interfaces is just one way of making the switch act like a router. Let's take a look now as an alternative approach to what we just did. And here we are going to focus on cat2. So let's redraw this diagram with slightly different look in mind. So remember, we have cat2, which is connected to cat1, which is connected to our Linux host. Now, I have connected Linux host to cat2 as well. So I have this connection, but now I'm going to turn this connection off here. So what I'm going to do now is, what I would like to do is I would like to ping from this interface here. I would like to ping this interface here. Now remember, this IP address here is 192.168.0.1, and the network that we are running here is 192.168.200.0/24. So this is what I'm going to configure. So this is going to be .100, but this interface here, this time around, I'm not going to configure it as a layer 3 interface. What I'm going to do here is I'm going to configure this as an access port, and then I'm going to configure that virtual interface that I called the SVI on cat2. And then I'm going to use this SVI interface to actually pass this traffic from my Linux box to cat1. Let's configure that. So I'm going to go to my terminal now, and I'm going to take a look at the configuration of my Fast Ethernet 03 interface. I can see here that this interface is shut down. Let's decide that we want to use, let's say, VLAN 200 for this purpose. So I'm going to create VLAN 200, and I'm going to go to interface Fast Ethernet 03. I'm going to say switch port mode access, switch port access VLAN 200, and let's just speed things up. I'm going to make this port a port fast, and I'm going to say no shutdown. Then on cat2, I'm going to say interface VLAN 200. So I'm going to create the SVI now, and I'm going to say IP address 192.168.200.255.255.255.0. At this moment here, if I do show interface VLAN 200, what I should be seeing is that interface is up and the line protocol is up. I should be able to ping my own IP address, and I should be able to ping my Linux box on the other side. From my Linux box, I should be able to ping my own interface, and I should be able to ping the switch on the other side. I should also be able to ping the switch 2's address, but at this moment, I should not be able to ping switch 1. Why am I unable to ping switch 1 here? Well, I'm unable to ping switch 1 for the same exact reason I was unable to ping switch 2 in the previous example, because here on cat2, I don't have IP routing enabled. So I am going to enable IP routing. But before I do that, let me remind you about one thing. Remember the default gateway we configured? Let me show you something. So now I'm going to say IP routing. So I have enabled IP routing. If I do show IP route, this is going to show me the default, this is going to show me my routing table, but take a look at this. It says gateway of last resort is not set. Even though in the previous output, before I enabled IP routing, I had the default gateway configured. Now, this is not the case. It is not the case because this command, IP default gateway, takes effect only if the device is operating as a host. When we start operating as a router, as a multi-layer switch, this command no longer has any effect. It is not going to insert the default route in the routing table. We don't need it at the moment. So what I'm going to do now is I'm just going to try to ping my switch 1. And in this case, this should be working. So let's spend a minute troubleshooting. Why is this not working? I can ping 2, but I cannot ping 1. And I just remember what the reason could be. The reason could be that now our cat1 doesn't have the route back to network 200. Well, let's fix that with the default route. So I'm going to show you now how to add the default route when the device is operating as a switch. So I'm just going to say IP route. And there we go. I have added the route back that now will take effect. Let me show you that. That will take effect when the device is operating as the router. So now we can see that we have a static route in place here. So now going to my Linux PC, I should be able to ping 192.168.0.1. So these were the basics of the multi-layer switching. Now we're going to go a little bit deeper in there and we are going to see how does this happen? How does this actually work from a theoretical Cisco Express forwarding perspective? So we are going to take a look at Ceph next.